Alright, trig class, in the next section we're going to look at vectors. So what is a vector? A vector is basically a direction and a magnitude. So I'm going to add into this grid here, let me blow this up so we can see it a little better. I'm going to add in a vector. So alright, let's say I start here at the origin and I'm going to add in a vector on top of this thing. Let's start at the origin, close as I can get. Let's make this vector go, let's make it go to here. And just to be able to see it a little better, I'm going to make this a little bit bigger. And let's make it red. Alright, so there's my vector. Alright, so what is the, the vector called? How would we describe this vector? This is a vector that from its starting point to its ending point, it points 2 units to the right and 1 unit up. Now, how do we write that? How can we describe that vector? What's a way that we can notate it? We can use this notation. We put a little, it looks like a less than symbol, but it's a symbol to let you know that you're dealing with a vector. And the first thing we write is the left or right component. So we go 2 units to the right, and then we go 1 unit up, and then we close it off. So it's kind of like, it's similar to the concept of a point. That's the point 2, 1. But if we are starting from the origin and ending at that point, then it's the vector 2, 1. Now the big difference between a point and a vector is I can pick this vector up and then move it, like say for instance there, and it's still the 2, 1 vector. And I can move it over here and it's still the 2, 1 vector. No matter where we start, we're moving 2 units to the right, 1 unit up. That's the 2, 1 vector, no matter where it is. It's easiest to see it and to know what we're going to call it if we make it begin at the origin, because then the terminal point of the vector ends up being just the point in the plane, and it would match this in this notation, other than just the endpoints, or the end symbols, but it would look the same. But the big thing is vectors in the plane can be moved around and not change their name. This is the 2, 1 vector, no matter where we set it down at. Alright, what is the magnitude of the vector? The magnitude of the vector, if you look at this, the magnitude of u is a squared plus b squared, where a is the horizontal displacement, that was our 2 in our last example. B is the vertical displacement, that's the 1 in our example. So 2 squared plus 1 squared. Well, let's look at this picture again. So this is the a, this is the b when we use this notation. And if I go back to here, and if you look right here, this is our 2, and this is the 1, this dashed line right here, and it's because this is just a right triangle. What's this? This would become the hypotenuse of that right triangle, and this would be the square root of 2 squared plus 1 squared. So once again, we've seen it so many times this semester, the Pythagorean theorem is at the heart of something that we're studying. So the magnitude of this vector, if we call this vector u, is the horizontal component squared plus the vertical component squared, and then we take the square root. It's literally because it is a Pythagorean theorem. Alright, what happens if we add vectors together? Well, if you think about this, I'm going to draw a little vector arrow on top of this picture. So on top of this, let's put a vector v. Let's say that's vector v right there. Alright, and once again I'll make it bigger anyway, so we can see it. Maybe not that big. And again, let me try to get as close as I can to being what it is. Now again, vectors can be picked up and moved anywhere in the plane. So what happens when we add 2 vectors together is we put the butt end of one vector at the head end of the other. So this is called the foot of the vector, the head of the vector, or the butt of the vector, the head of the vector. If we put where one ends right up next to where the next one begins, that combination from here to the tip end of this one is what we call the resultant vector, and it literally is the sum of those two vectors. So if I start down here and I go to that point, that vector is, let's make it red and thicker. That red vector is our resultant vector, and that red vector is the sum of u and v. Alright, now I'm going to set this resultant, the sum vector, I'm going to move it over here to the side. Alright, and I'm going to take, there's v, I'm going to outline u on top of v. I'm sorry, I'm going to put u, a vector on top of u, and now I'm going to pick it up, and remember we're adding, first we did u plus v, so I put v on the tip end of u. So what I did the first time was put v on the tip end of u, and then this fit on top of it. That was the resultant vector. And what I want you to see now though is if I reverse it and I start with v, so I start from this point and move in this direction, and then I add u to that, so like the reverse of this, that would put the tail end of u onto v. And now if I start, I'm trying to get this as close as I can, if I start from the tail end of v and go to the end of u, I would get the exact same thing. Okay, and what this is supposed to illustrate is that vectors behave very similar to numbers. And what I mean by that is, 5 plus 2 is 7, and 2 plus 5 is 7. Alright, you get the same thing, it doesn't matter. Well, with vectors, the vector that I get when I add u plus v is the same thing as the vector I would get if I add v and then u. So vectors can be combined in any order. And the other thing that I want you to see is the sum of two vectors is a vector, which makes sense. Okay, I add two vectors together, I get another vector, and the order I add the vectors doesn't matter. Alright, so if you look at this, there's a lot of properties of vectors that behave just like numbers. And what I mean by that is if you add two numbers together, the order doesn't matter. If you're adding three numbers together, you can add in any order. So I could add the second and the third, and then add the first, or I could add the first and second, and then add the third. I would get the same vector. Okay, just like if this was 1 plus 2 plus 3. Well, 2 plus 3 is 5, plus 1 is 6. 1 plus 2 is 3, plus 3 is 6. We get the same thing, and it's going to work out with vectors as well. Alright, there's something called the zero vector that you could add to any vector and get back to the vector you started. And for every vector, there's an opposite. So what do I mean by that? What do I mean by every vector has an opposite? Well, every non-zero vector, I should say, if you leave the origin and you go on this vector, so we go -4 to the left and then up 3. So left 4, up 3. Well, what would be the opposite of that? The opposite of left 4 and up 3 would be right 4 and down 3. And since these two vectors are opposite, what happens if I add them? Well, remember, I go to the tip end of one, so let's say I go to the tip end of the blue one, and then I come back with the tail end back to the head, and where do I end up? I end up right back at the origin. So these vectors cancel each other, and that's exactly what this property here is saying. So every non-zero vector has an opposite, and opposites combine to 0, just like with numbers. Okay. Multiplications, a and b here represent scalars. These are vectors. Scalars just mean numbers that make vectors bigger and smaller, like stretch them or shrink them. So this is multiplying through by scalar, what do we do if we add two vectors and then multiply by the scalar? It's the same thing as multiplying by the scalar to each vector and then adding. Alright, and then this also shows that if we have two vectors that two scalars we're adding together and then multiplying by a vector, we could multiply each scalar by the vector individually and then add the two together. So it's like the distributive property. It looks just like the distributive property. Alright, and then associative property with scalars and vectors. And just like there is what we call an additive identity with vectors, this is a multiplicative identity. Like if we multiply a vector by 1, we don't change the vector. If you multiply a vector by 0, you get the 0 vector. If you multiply a scalar by the 0 vector, you still get the 0 vector. Alright, remember these double bars mean magnitude, the length of the vector. What's the length of a vector after I scale it? It's the length it was before we scaled it times the scalar. So what does that mean? So here's the vector 1, 2. Right? If I double the length of this vector, it would literally mean copying and pasting it right on the end of it. Alright, so I doubled the length of the vector. I doubled its magnitude, which is what this is saying right here. If you if you multiply a vector by a scalar, it literally is, it's like taking the magnitude of the old one and multiplying whatever that magnitude was by the absolute value, because again, you could negate, if you do a negative, it goes back in the opposite direction, like we've seen. But so that's the absolute value of that. But that's what this is suggesting, that if you take a vector and you scale it, make it longer, make it shorter, the new magnitude of the scaled vector is the magnitude of the vector before you scaled it times whatever you scaled it by. Alright, let's look at some operations. So we got these two vectors. We want to see what does negative 2u look like. 3u plus v and u minus v. Alright, so let's start with the first one, negative 2u. So this is u, and that would mean this is negative u. Negative u goes back in the opposite direction of u. Alright, and if this is one of those, then two of them would literally mean one stacked on top of the other. So copy paste. So that's 1u, that's 2u's. It's close as I can get them together. But literally, negative 2u means we're going the opposite direction of u and we're doubling the magnitude. But what we got to understand is it's not two vectors. So we would just put one over top of this, and that would be how long it is. Alright, and then again I'm going to make it bigger. Let's do blue. And there. So this would be negative 2u. So it literally just means double it and negate it, meaning go in the opposite direction. So there is negative 2u. Alright, I'm going to stick that up here with this one. Alright, 3u's and a v. Okay, so there's 1u. Control C, Control V. There's 2u's. Again, try to put tip to tail. And then there's a third one. So there's the 3u part of this. Right? And now to that we add v. So after we've added the 3u's, these are all positive, so we don't change direction, we add v. So this is v right here. Alright, and so there is v. So remember, I have to put this on the tip end of these 1, 2, 3 u's. So I'll stick it right there. And then I connect them together. So once again, I start here and I'll end at the tip end there. Alright, so there is 3 u's plus a v. All right, I'll stick it in here. I'll show you what we do with all these in just a second. All right, and then finally for the last one, we need 1 u, and again, this is a u right here. All right, this is a u, so 1 u minus v. So this is v. So basically, what happens if you negate it? It's like rotating in 180 degrees. So I'm going to click on here and just tell it to rotate this 90 and 90 again. And so now I'm v back in the other direction. All right, so u minus v, so this is positive u, and from the tip end of that, I'm going to do minus v, and then I'm going to connect the back end of the u vector to the tip end of the minus v vector. All right, let's do that one red, and all right, and so there is u minus v. All right, now I cleared off everything, just these 3 final resultant vectors that we got when we did the scaling here, the resultant of these 2 vectors once this one was scaled, negating this one, adding this one. And I want you to see mathematically what's going on here, and you're going to see that this is very easy to do analytically. You don't have to have a grid and draw all these. You can just do it mathematically. All right, so what is the u vector? Well, notice right here, what do? We went from 0 to 1. We didn't go up or down. So we went 1 in the x direction. We went none in the y direction vertically. So that's what u is. Well, look at negative 2u. Look at this vector. What does it do? Put it in the grid. It starts at 2 and it goes back to 0. So it just moves us 2 units in the negative x direction. So what is negative 2u? It was negative 2, 0. So what did we do to u? We negated the only one that's non-zero. We negated that one. All right, but you'll be able to see it a lot easier with these other 2. All right, now let's look at this one. 3u plus v. All right, so u was 1, 0. V was negative 1, negative 2. Let's look at 3u plus v. What happens if I grab 3u plus v and I put it into the grid? I'm going to move it here. I'm going to make it start it at 3 on the y-axis. So that's starting at 3. And what happens? I get to this point. I get to the point 2, 1. When I'm starting at 3, 0. So what's happening? I'm moving down 2 units from 3 down to 1, and I'm moving right 2 units. So right 2 units and down 2 units. So 3u plus v, what we just put on here, this black vector, is 2, negative 2. We go right 2, we go down 2. All right, right 2, down 2. But if you look, 3u, well, here's u. What is 3u? We just saw that negative 2u was negative 2, 0. Well, what do you think 3u is going to be? It's going to be 3, 0. And then if I add v to 3, 0, if you imagine this being 3, 0, that's 3u. And then combine this and this and this, I get 3 plus negative 1 is 2. 0 plus negative 2 is negative 2. Literally all we have to do with these is just, it's like order of operations. We just multiply this vector by that number. All the components, all the numbers we see, we multiply by that number, and then we add component wise, like x to x, y to y, the stuff there. So let's start off doing that on this last one, u minus v, and then show that that is what we get with the red vector. Alright, so u minus v, we start off with the 1, 0 vector, and we're going to subtract the v vector, which is -1, -2. Right? Just like with numbers, and that's what I've been saying, that this behaves just like numbers. Subtracting a negative is like adding a positive. And so what do we get? We're going to get 1 plus 1. Here is 2. And then 0 plus positive 2 is also 2. We get the 2, 2 vector. So is this the 2, 2 vector? If I move it in there, we see, yeah, it is. 2 to the right, 2 up. So all we have to do with these things is, if we can write them in their components form, we can then just do the math, come up with a new vector and plot the new vector, if we even need to plot the new vector. Sometimes we don't need to. We just need to come up with what the vector would be. So if we want to do these operations, not by dragging around little arrows in a plane, we can do it component-wise. These numbers within the vector are called the components: horizontal component, vertical component. So how do we add these things? We add component-wise. X components to X components, Y components to Y components, or horizontal to horizontal, vertical to vertical. And then how do I scale? I just multiply each number in there by the scalar.